All right. Hello, everyone. My name's Arpad. I'm also known as Swatinem Online. And I keep a blog. You may have come across it through This Week in Rust. Professionally, I work for Sentry, where I do the Rust SDK and also the whole processing pipeline. And today, I will take you on a journey, and we will dive deep into the Rust compiler and see how an async function makes its way through the Rust compiler and then into your final binary. Speaking of compilers, compilers are essentially a step of transformations. So there is a couple of data structures, and these are the ones for the Rust compiler. We start out with an abstract syntax tree, which is very close to the code you're actually writing. And then your code makes it through a high-level intermediate representation, mid-level intermediate representation, before it then goes into code gen, which by default is LLVM, but there's also other backends. And let's start with a very simple async function, the simplest we can write. And let's do the first transformation from the syntax tree, from the stuff that you're writing in your editor, to, well, the first intermediate representation in the compiler. And Nico might have spoiled you a bit in the last talk that essentially async functions is just a lie. They don't really exist as such in the compiler, but they're only sugar for a function that returns a future and internally has an async move block inside. And here we can also see in the example that if you have an argument, the async move block explicitly captures all of the arguments that you give your async function, which we will also see examples of later on. And well, this is pretty much exactly the opposite of what Clippy would tell us. So, well, sorry Clippy. And the first thing we might notice here that even though async functions and functions returning futures are basically the same, there is a subtle difference between the two. The first one is that an async function is guaranteed by compiler logic to be fully lazy, so it calling the async function doesn't do anything, versus a function that just happens to return a future can do some stuff. So there's a big difference between calling an async function and then later on actually awaiting it. Worst case, you can have fully synchronous code that can do anything at once, and then in the end, it just happens to return something that's a future. This can have some consequences. For example, if you're using chaining APIs or extension traits on the future. One example here might be from the futures crate, if you want to make your future catch unwind. This doesn't really work that well if calling the async function does different work than actually awaiting it. And there's a couple of workarounds here that we can use. We can recognize the fact that there's a difference between calling it and awaiting it and handle these two cases separately. So we catch unwind first the call of the async function and later on the await again. Or we can also do it a bit simpler by just wrapping everything up in an async move block. That way, it is really guaranteed to be completely lazy and not do anything. Other examples where this might be problematic is, for example, if you want to instrument an async function with tracing, or also with a Sentry Rust SDK. And especially in this case, I'm calling this out because I got burned by this pretty bad myself. I had a memory leak related to a function that was not lazy enough. And as Nico already showed you the future, which is async functions and traits, here I thought, well, the current plan is to really have async functions and functions returning futures be interchangeable. And at first I thought, well, this isn't really a good idea because you're missing these hard guarantees that things are actually really lazy. But then yesterday when I couldn't fall asleep, I noticed that, well, even the tracing instrument macro is transforming an async function into a function that first creates a tracing span and then returns an async block instrumented with that span. So there is transformations in the compiler and in some macros that, well, break this rule a little bit. All right, enough from this small detour. Let's get back to our async function, or rather our function returning an async block. And this here is still a very simplified view of things. In reality, it's a bit more complicated, and as far as I understand, and the types team might correct me later on, it looks more like a type alias infiltrating. So you have some opaque type that implements future and also captures all of the lifetimes, which, as we have heard, might change in the future as well. All right, so we arrived at this thing, and we can actually look at it in detail with an unstable compiler flag. So if you have the nightly compiler, you can actually look at the here output specifically with this compiler flag. And what we see here with an older Rust version, 166, that we see this from generator here. And what actually does this mean? This lang equals from generator means that this is something that the compiler specifically knows about. And in this case, it used to be a function and some associated types and structs that were defined in the standard library. And this is what basically the from generator function used to look like. It defined a wrapper, like just a struct with a generator inside and an impl for future for it. And this was kind of a leaky abstraction, and it showed up everywhere. So if you're running your tests and you're panicking, you see it in your console everywhere. Every second line is just from generator GenFuture. Same thing if you want to profile, for example, in the great Samply profiler, every second line used to be GenFuture. Same thing also in Sentry. This is really hard to read if you want to debug something, and every second line is just GenFuture. So I thought to myself, can we do any better? And I kind of challenged myself to do better here. And to understand what I did, let's look at what a generator is from a trait perspective. And that's a simplified version of what the generator trait is. And it looks very similar to the future trait, doesn't it? We can actually arrive at the future trait with some simple replacements here. First things first, we have a generic argument for a resume type, and we can just fill in an end mute context here. Second thing is we are not yielding any values really, so we can just remove this associated type. And last but not least, we just rename a couple of things, and we're left with the future trait. So it's really that simple. It shouldn't be any harder for the compiler itself. So essentially, in the compiler, we have this special generator that's a special compiler type, which just happens to impl the generator trait with some compiler logic, some compiler magic. And what we need to do is we need to teach the compiler that, hey, I have this other special generator that's actually some async block that's also special to the compiler and that just happens to impl future. And with that, we can have great stack traces in your console, in Sentry, and as a bonus, we also improved compile times, although that's just some synthetic benchmarks, so it does not reflect the real-world code that much. So we're basically all done, right? We can go home, can't we? But it wasn't quite that simple, because there were some lifetime errors associated with all of this. Turns out I went a bit too far just teaching the compiler to have some special async type that implements future, and yeah, another lifetime error that happened during this time. I was thinking, well, what did I do wrong? or how can I change it in some way that it actually works, that it does not break the compiler test suite? And to give you a hint, here's the output from Rust 67, where part of this landed. And you can see two things here. Instead of the from generator thingy, we have an identity future. And we also have an explicit resume type mentioned here. So this identity future, it's pretty much what you would imagine. It's just a function that future thing goes in, future thing comes out, and type lifetime error just magically disappears. And this resume type is also an interesting thing, because ideally, we would want to have the context here. But instead, we have the resume type and an associated unsafe getContext method, which is basically just a wrapper around the context, but without any lifetimes in it. And the lifetimes basically appear out of thin air using this getContext method. So where is this actually used? It is being used when the compiler is lowering the await keyword, and the await keyword gets expanded to this whole chunk of code. And here we can see our getContext, and we can also see that a generator internally that does not have await, but it has a yield statement instead. Okay, getting back to identity future. So why was it needed? And to this day, I don't really know the full details of why it was needed, but doom scrolling through the open PRs of the Rust project, I noticed this pull request with a weird title that didn't really say anything to me. But it mentioned that it fixed a bug which detailed the same lifetime errors that I was getting with my refactorings. And it also mentioned that seemingly insignificant tweaks, like adding an identity function, suddenly make it compile. As far as I understand, there was some logic that the order in which you define some lifetimes matters, and putting it through an identity function somehow changes this order and makes it compile. I'm not quite sure. But yeah, fast forward, Rust 170, identity future is gone. Now there's a lot cleaner code here. So let's take some time and recap. What did we learn so far? The cake is a lie, or rather, async functions as such do not really exist in the compiler. It's all just functions that return a future. But we've also seen that this can cause problems if you're not careful enough about it. We've also learned that internally in the compiler, we're not talking about generators that have yield instead of await. We've learned about some nightly compiler flags that you can use to have a look at all of this stuff yourself. And we've learned that the compiler is really complex and always changing, and that also compiler contributors are struggling with lifetime errors like everyone else does. But we also left with some more functions, like what is this generator here? And to work up to the answer to this question, let's try to implement our own future. And the simplest thing we can do here is we define an enum which has two states, unresumed, holding some form of data, and finished. And we can implement the poll function of future here. That's very simplified view. In reality, it might be a bit more complex. And what we're doing here, we basically match on the enum. If it holds data, we return this data and change the state of the enum. And if it's already finished, we're panicking. So to summarize, in the compiler itself, it's also quite similar. So everything is just a state machine. And all this logic is implemented when we're moving from the here intermediate representation to the mere. And we can also have a detailed look into this using another nightly compiler flag. And this is also a very simplified view of the mere output. We can see here we have a discriminant, and we are switching on this discriminant, which is basically the mere equivalent to a match statement. And there's a couple of branches. There's the normal branch when you actually want to return data. There is one branch that panics after you poll the future when it's already completed. And there's another branch that panics when the future is poisoned, because futures are being poisoned after, when they experience a panic. All right, so we have our own enum implemented, and it holds some data. Remember very early on, I showed you this example where an async function explicitly captures all of the arguments you give it, and they end up in this enum somehow, which, if you pass large amounts of data into this, for example, hey, I have a buffer, like 1 kilobyte buffer, then my future ends up being exactly the size of this. And we can use another nightly compiler flag to actually view all of this in much more detail and get a look at all of the different enum equivalent variants here. For example, unresumed, returned, panicked, and so on. And we can also see explicitly what kind of data do they hold. And this is especially important if you have an async function which takes another async function as input. And the problem here is that whatever this outer async function is doing, it might end up in a situation where it's doing some loops, some matches, some if else, whatever. And you end up in a situation where the outer future is actually a couple of times larger than the future you pass in. There's a couple of workarounds you can do here. Pin box might be an obvious solution, or just pin on the stack, which just makes it a simple pointer. You still have the problem that the outer future might grow by some factors, but at least the amount by which it grows is a lot lower. One success story to call out here is that working together with the author of the amazing Mocha crate, we were able to use some of these workarounds to reduce like a growth factor of 7 times to something that's more reasonable. Okay, let's do another recap. So what we've learned now is that generators are basically just state machines and just big enums, and it's all just a match statement transitioning from state to state. And we've learned about some more nightly compiler flags that you can use if you are interested to really dive deeper into this stuff. We can look at the mere output, we can print the type sizes, and we've seen that this size off might be a problem in some cases. So let's take a look into the future. So what's the future of future? Some of these problems that we've seen, for example, the size of problem, that's something that's well known to the Rust compiler community itself. And there have been multiple attempts throughout these years to actually solve this, to optimize the compiler in such a way that a future doesn't grow by a factor of 7 if you put in another future from outside. And so far, none of these attempts have succeeded. There is a promising pull request open, but it's also stalled for, I believe, half a year with no visible progress on the outside. But I'm really hopeful that it will be solved eventually. And for myself personally, what I would like to do is I would really love to get rid of this resume tie indirection. But it's, I don't know, it's very complicated, and I don't really have a concrete lead how to really solve this thing. And another thing that I challenge myself with is to solve demangling. So what is demangling? Let's look at this example here. So we have an async function, which through some logic has an embedded closure in it, which then also has an async block in it. And on Windows, we get this clear distinction. So the function name of the innermost future, so what appears in the stack trace, it has clear names. It's an async function inside a closure, and then there's, it's an async block inside of a closure, inside of an async function. But on Linux and Mac, it all just says closure, closure, closure. So debugging your code and figuring out what is actually happening gets a lot harder with this. And this thing actually got more traction in recent days, and I'm hopeful to be able to solve this problem. With this, I'm very optimistic for the future of futures. As you've seen, they're changing constantly. The inner workings of future itself has changed over the past year, and there's also some changes ahead. And with that, I would like to end my talk. Thank you.